target. Let us begin with the vectors in R3. How to represent a vector in R3? Let us choose a vector x cap equals a triplet x1, x2, x3 in R3. We have learnt that this vector x cap in R3 can be written as x cap equals x1 I cap plus x2 j cap plus x3 k cap. Here in our new notation, we take I cap equals E1, j cap equals E2 and k cap equals E3. Now x cap can also be written as x cap equals x1 E1 plus x2 E2 plus x3 E3. This can also be represented by using summation symbol. X cap equals summation sigma over I xi ei. Here the index I takes the values 1, 2 and 3. If we expand this summation, we get our previous notation x cap equals x1 E1 plus x2 E2 plus x3 E3. Here E1 equals I cap and I cap equals the triplet 1, 0, 0, which is the unit vector in the direction of the positive x-axis. E2 equals j cap equals 0, 1, 0 and j cap is the unit vector in the direction of the positive y-axis. Similarly, E3 equals k cap equals 0, 0, 1 and it is the unit vector in the direction of the z-axis. So, every vector x cap equals x1, x2, x3 or x cap equals x1 I cap plus x2 j cap plus x3 k cap in R3 can be represented as x cap equals summation sigma over I xi ei. Now, let us consider a vector field f from R3 to R3. Since f is a vector field from R3 to R3, we can write f equals f1 I cap plus f2 j cap plus f3 k cap. We know very well that f1, f2 and f3 are component functions of the vector field f. Here in our new notation, f equals f1 E1 plus f2 E2 plus f3 E3 because I replaced I cap with E1, j cap with E2 and k cap with E3. Now, f can also be written as f equals summation sigma over I fi ei. We have to observe here that I, j, k are indices. They take values 1, 2 and 3. But I cap, j cap and k cap are unit vectors in the directions of x-axis, y-axis and z-axis respectively. We have to observe this difference. I have already mentioned one thing that we require these notation to write the proofs of vector identities in a compact way. For that purpose, let us choose a scalar field phi from R3 to R now. Now, let us suppose that all the partial derivatives of this particular scalar field phi from R3 to R exist. Let us write dou phi by dou x equals dou phi by dou x1. That means I replaced x with x1. Next, let me represent this dou phi by dou x1 as dou 1 phi. Hence, dou phi by dou x can be written as dou phi by dou x1 and then it can be represented as dou 1 phi. So we must understand one thing. Whenever we have to write dou phi by dou x, we write dou 1 phi. Similarly, dou phi by dou y can be written as dou phi by dou x2. We represent this dou phi by dou x2 by using the symbol dou 2 phi. So, dou phi by dou y can be replaced with dou 2 phi. Similarly, dou phi by dou z can be written as dou phi by dou x3 by replacing z with x3. This can be written by using a simple symbol dou 3 phi. So, our partial derivatives dou phi by dou x, dou phi by dou y and dou phi by dou z of the scalar field phi can be rewritten by using a new notation dou 1 phi, dou 2 phi and dou 3 phi respectively. By using this new notation, how to write the gradient? Let us take the gradient of the given scalar field phi from R3 to R. Grad phi or del phi equals dou phi by dou x I cap plus dou phi by dou y j cap plus dou phi by dou z k cap. This dou phi by dou x can be replaced by dou 1 phi. Dou phi by dou y is replaced with dou 2 phi and dou phi by dou z is replaced with dou 3 phi. Of course, I cap equals E1, J cap equals E2 and K cap equals E3. Now, grad phi takes a new form, that is grad phi equals del phi equals dou 1 phi E1 plus dou 2 phi E2 plus dou 3 phi E3, that equals summation sigma over I dou I phi ei. Here I takes the values 1, 2, 3. Here comes our first tool, the Kronecker delta. The Kronecker delta is defined by delta suffix ij equals 1 if I equals j. Delta ij equals 0 if I not equal to j. That means delta 11, delta 22 and delta 33 equals 1. all the remaining values delta 12, delta 13, delta 21, delta 23, delta 31, delta 32 are 0. By using this Kronecker delta ij, we can write a 3 by 3 matrix which is called the delta matrix. The delta matrix is given by delta equals a 3 by 3 matrix delta 11, delta 12, delta 13 on the first row, delta 21, delta 22, delta 23 on the second row, delta 31, delta 32, delta 33 on the third row. If we substitute the values of the Kronecker delta suffix ij, this delta matrix becomes the identity matrix. That means delta equals 1 0 0 0 1 0 0 0 1. This Kronecker delta helps us to represent some vector functions in a crisp fashion. The next tool is the Levi-Civita tensor. It is also called the Levi-Civita symbol. What is the definition of this Levi-Civita tensor? Let us see. It is denoted by the symbol epsilon suffix ijk. It is defined by epsilon suffix ijk equals 1 if the indices I, j and k are in a cyclic rotation in the clockwise direction. Epsilon suffix ijk equals -1 if the indices follow the cyclic rotation in the anti-clockwise direction. If any two indices repeat, epsilon ijk equals 0. So this Levi-Civita takes three values 1, -1 and 0. Epsilon ijk equals 1 if ijk follows cyclic rotation. Epsilon ijk equals -1 if ijk are in the anti-clockwise rotation. It is 0 in all the remaining cases. Let us understand this Levi-Civita tensor in a more precise way. Consider a circle having the numbers 1, 2, 3 in clockwise direction. If 1, 2, 3 are in clockwise direction, then first start at 1, next go to 2 and reach 3 in the clockwise direction. Then we can write epsilon suffix 1, 2, 3. Its value is 1. So epsilon suffix 1, 2, 3 equals 1. If you start at 2, you have to go in a clockwise direction 2 to 3 and 3 to 1. So epsilon suffix 231 is also equals 1. If we start at 3, we have to go to 1 and then to the number 2. Hence, epsilon suffix 312 equals 1. Hence, epsilon suffix 123, epsilon suffix 231, epsilon suffix 312 are equal to 1. In the anti-clockwise direction, if we consider the numbers 1, 2, 3 on a circle, we have to write the values of the Levi-Civita epsilon suffix ijk. If we start at 3 and go to 2 and then to the number 1 in the anti-clockwise rotation on a circle, we have epsilon suffix 3 to 1 is equal to -1. If we start at the number 2 and if we move in the anti-clockwise direction to the number 1 and then to the number 3, then epsilon suffix 2 and 3 equals -1. If we start at 1, we have to move in the anti-clockwise direction to the number 3 and then we have to reach 2. Then epsilon suffix 132 equals -1. So epsilon suffix 321 equals epsilon suffix 213 equals epsilon suffix 132 equals -1. In the remaining cases, epsilon suffix 111, epsilon suffix 222, or epsilon suffix 333, or epsilon suffix 112, or epsilon suffix 223, etc. The value of the Levi-Civita is 0. Here we can observe one thing. The indices repeat. That means in epsilon suffix ijk, if I repeats twice, or if j repeats twice, or if k repeats twice, or if they repeat thrice, or in any other case, this Levi-Civita takes the value 0. As a whole, the Levi-Civita equals 1 if 1, 2, 3 are in clockwise direction rotation, and it is equal to -1 if the numbers 1, 2, 3 are in the anti-clockwise direction. In all the remaining cases, its value is 0. This Levi-Civita is very useful in representing our vector functions like curl of a vector field, etc. The Levi-Civita tensor satisfies a few properties. The first property is epsilon ijk equals epsilon jki equals epsilon kij. We followed the clockwise rotation by taking I, j, k on a circle in this property. Our next property is epsilon ijk equals minus epsilon jik. Observe here that we interchanged the positions of I and j indices. That means if I flip the indices I and j, we get a minus sign. So epsilon ijk equals minus epsilon jik. Similarly, if we take epsilon ijk and if I flip the positions of j and k, I get minus epsilon suffix ikj. So epsilon suffix ijk equals minus epsilon suffix ikj. The third property is a very useful and important property. Epsilon ijk times epsilon imn equals delta jm delta kn minus delta jn delta km. This is a relationship between the Levi-Civita and the Kronecker delta symbols. I have already represented the gradient of a scalar field previously. Now let me represent the divergence of a vector field. For this purpose, select a vector field f, which can be written as f equals f1 I cap plus f2 j cap plus f3 k cap. Here f1, f2 and f3 are the component functions of the given vector field f. Suppose that all the partial derivatives of these functions exist. Now let us write the divergence of the given vector field f. Div f equals dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. We know this already. Now replace x with x1, y with x2 and z with x3. Then div f equals dou f1 by dou x1 plus dou f2 by dou x2 plus dou f3 by dou x3. But I have written dou f1 by dou x1 as dou 1 f1. Similarly, I have written dou f2 by dou x2 as dou 2 f2. Next, I have written dou f3 by dou x3 as dou 3 f3. If I substitute these symbols, we obtain div f equals dou 1 f1 plus dou 2 f2 plus dou 3 f3. This can also be written as div f equals summation sigma over I dou I fi. If we expand this summation, we get back our representation div f equals dou 1 f1 plus dou 2 f2 plus dou 3 f3. But I want to represent this divergence of the given vector field by using the Kronecker delta symbol. How to write the divergence of a given vector field by using the Kronecker delta? Let's see. Div f equals summation sigma over I summation sigma over j delta sub ij dou I fj. This is a new representation of the divergence by using the Kronecker delta. Here the indices I and j take the values 1, 2 and 3. Previously, I started with a vector field and the old divergence formula, and I have written the divergence by using the Kronecker delta. Now let us verify whether this representation of the divergence by using the Kronecker delta is equal to our old divergence formula or not. So let us start with the divergence of the given vector field by using the Kronecker delta. Div f equals sigma over I, sigma over j, delta suffix ij, dou I fj. This is our new notation for the divergence of the vector field f. Let us expand this summation. First, if we expand this by taking I equals 1, I equals 2, I equals 3 and j equals 1, j equals 2 and j equals 3, we get div f equals delta 1 1 dou 1 f1 plus delta 1 2 dou 1 f2 plus delta 1 3 dou 1 f3 plus delta 2 1 dou 2 f1 plus delta 2 2 dou 2 f2 plus delta 2 3 dou 2 f3 plus delta 3 1 dou 3 f1 plus delta 3 2 dou 3 f2 plus delta 3 3 dou 3 f3. Here delta 1 1 equals 1, delta 2 2 equals 1, delta 3 3 equals 1, but the remaining deltas delta 1 2, delta 2 1, delta 3 1 etc. are all equals 0. So this expression reduces to delta 1 1 dou 1 f1 plus delta 2 2 dou 2 f2 plus delta 3 3 dou 3 f3. If we plug in the values of delta 1 1, delta 2 2, delta 3 3 here, what do we get? Div f equals dou 1 f1 plus dou 2 f2 plus dou 3 f3, because delta 1 1 equals delta 2 2 equals delta 3 3 equals 1. This is nothing but our original divergence of a vector field formula. Div f equals dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. So div f equals sigma over I, sigma over j, delta ij, dou I fj is another representation of the divergence of a vector field. This Kronecker delta representation of the divergence of a vector field is very useful in writing the proofs of so-called vector identities. Now it is the turn of curl of a vector field. So I would like to represent the curl of a vector field by using the Levi-Civita symbol. For this purpose, let me choose a vector field f from R3 to R3 given by f equals f1 I cap plus f2 j cap plus f3 k cap. Here f1, f2 and f3 are the component functions of the given vector field f. Suppose that all the partial derivatives of these functions exist and they are all continuous. Under these assumptions, let's write down the curl of the given vector field. We know that curl f equals del cross f equals a 3 by 3 determinant I cap, j cap, k cap on the first row, dou by dou x, dou by dou y, dou by dou z on the second row, f1, f2, f3 on the third row. But in our new notation, dou by dou x takes the form dou1, dou by dou I equals dou2, dou by dou z equals dou3. Hence, curl F equals I cap, j cap, k cap on the first row, dou1, dou2, dou3 on the second row, f1, f2, f3 on the third row. If we expand this determinant by using the first row, we get curl F equals I cap times dou2 f3 minus dou3 f2 minus j cap times dou1 f3 minus dou3 f1 plus k cap times dou1 f2 minus dou2 f1. In the second term, multiply the expression in the brackets with the minus sign. So curl F equals I cap times dou2 f3 minus dou3 f2 plus j cap times dou3 f1 minus dou1 f3 plus k cap times dou1 f2 minus dou2 f1. Here we have the I cap coefficient, the j cap coefficient and the k cap coefficient. They are the components of the curl F. Let's represent the components of curl F by using the symbols C1, C2 and C3. So here C1 equals the coefficient of I cap, that is C1 equals dou2 f3 minus dou3 f2. C2 equals the coefficient of j cap, that is C2 equals dou3 f1 minus dou1 f3. The third component C3 equals dou1 f2 minus dou2 f1. Let me represent the components C1, C2, C3 of the curl F by using the Levi-Civita tensor. How to represent the components C1, C2, C3 by using the Levi-Civita? Let us see. The first component C1 of curl F can be rewritten as C1 equals sigma over j, sigma over k, epsilon sub 1jk dou j of k. The second component C2 can be represented as C2 equals sigma over j, sigma over k, epsilon sub 2jk dou j of k. Similarly, the third component C3 of curl F can be represented as C3 equals sigma over j, sigma over k, epsilon sub 3jk dou j of k. Thus, we can represent the components C1, C2, C3 by using the Levi-Civita tensor. Let's see whether these are equal to our previous notation or not. For example, let us consider the first component C1. C1 equals summation sigma over j, summation sigma over k, epsilon sub 1jk dou j of k. Here j and k take the values 1, 2 and 3. To expand this, let's fix k and expand the summation over j by taking j equals 1, j equals 2 and j equals 3. Then this expansion equals epsilon sub 1 k dou 1 fk plus epsilon sub 1 2 k dou 2 fk plus epsilon sub 1 3 k dou 3 fk. Now we need to expand over k. That means we have to substitute k equals 1, k equals 2 and k equals 3 in this expression. In the expression we have 3 terms. Let's first consider the first term epsilon sub 1 k dou and fk. Here if we take this, because 1 repeats twice, epsilon sub 1 k equals 0. So epsilon sub 1 k dou 1 fk equals 0. So the first term vanishes. We left with 2 terms only. Now let us take the second term, that is epsilon sub 1 2 k dou 2 fk. Here if we put k equals 1, epsilon becomes epsilon 1 to 1, that is 0 because 1 repeats twice. If we put k equals 2, epsilon becomes epsilon sub 1 to 2, that is also 0 because 2 repeats twice. So we are forced to substitute k is equal to 3 only. So this second term becomes epsilon sub 1 to 3 dou to f3, because in epsilon 1 to 3 the indices are in the cyclic rotation, its value is 1. If we substitute epsilon 1 to 3 equals 1, the second term becomes dou to f3 only. Now let us go to the third term. The third term in this expansion is epsilon suffix 1 3 k dou 3 fk. If we put k is equal to 1, epsilon becomes epsilon 1 3 1, it is 0. Similarly, if we put k is equal to 3, we get epsilon suffix 1 3 3 and it is also 0. So we are forced to substitute k equals 2 only. So the third term becomes epsilon sub 1 3 2 dou 3 f2. Here the indices are in the anti-clockwise rotation. So epsilon 1 3 2 equals minus 1. So the third term becomes dou 3 f2. All over, the expansion of C1 gives us C1 equals dou 2 f3 minus dou 3 f2, which is nothing but our previous C1 representation, which was the coefficient of I cap in the expansion of curl F. In the same manner, we can obtain C2 from the new representation, and also we can bring back C3 from our new representation of the components by using the Levi-Civita symbol. Now the representation of the components is over. Now let us go to curl F expansion. Already we have written curl F by substituting C1, C2, C3 components. Curl F equals C1 I cap plus C2 j cap plus C3 k cap. But we need to replace I cap equals E1, j cap equals E2 and k cap equals E3. Then curl F equals C1 E1 plus C2 E2 plus E3. This is again equals summation sigma over I CI. Ci means a general component, the ith component. If you put I equals 1, we get C1. If we put I equals 2, we get C2. If we put I equals 3, we get C3. In general, the ith component of curl F, C sub I equals summation sigma over J, summation sigma over K, epsilon sub ijk dou I fk. If we replace this here in the place of Ci, we get back the representation of the curl F. Curl F equals sigma over I, sigma over J, sigma over K, epsilon sub ijk dou J fk. Let us turn our attention to the representation of the cross product and the dot product. We can represent the dot product of two vectors by using the Kronecker delta. Also, we can represent the cross product of two vectors by using the Levi-Civita tensor. Let's see how to represent those dot product and cross product of two vectors. Let's choose two vectors a cap equals a1 I cap plus a2 j cap plus a3 k cap and b cap equals b1 I cap plus b2 j cap plus b3 k cap. These two are two vector fields or any two vectors. Now let us take the dot product of a cap and b cap. If a cap is dotted with b cap, what do we get? A cap dot b cap equals a1 I cap plus a2 j cap plus a3 k cap dotted with b1 I cap plus b2 j cap plus b3 k cap. It equals a1 b1 plus a2 b2 plus a3 b3. We get the same effect by using the Kronecker delta representation. A cap dot b cap equals sigma over I, sigma over j, delta sub ij, a sub I, b sub j. Here the indices I and j take the values 1, 2 and 3. If we expand these summations, we get back the dot product a cap dot b cap equals a1 b1 plus a2 b2 plus a3 b3. Similarly, we want to represent the cross product of two vectors a cap and b cap by using Levi-Civita. In general, a cap cross b cap equals, it's a 3 by 3 determinant I cap, j cap, k cap on the first row, a1, a2, a3 on the second row, b1, b2, b3 on the third row. This we know very well. Now let us represent the same cross product by using our Levi-Civita symbol. The new representation of the cross product is a cap cross b cap equals summation sigma over I, summation sigma over j, summation sigma power k epsilon sub I j k a suffix j b suffix k. If you expand this, we get back our cross product again. So far, we have seen how to represent vectors in R3, scalar fields, vector fields, the gradient of a scalar field, the divergence of a vector field, curl of a vector field, so on, so forth. I hope I am clear with all the notation. I would like to suggest you to be familiar with all the notation which we have seen already. Now, I have listed out all the vector identities which I am going to prove. I picked up 9 vector identities to prove in this lecture. Our first vector identity is curl of grad phi equals 0 cap the origin. In this vector identity, phi is a scalar field. The gradient of phi is a vector field. So we can apply curl on that vector field grad phi. Curl grad phi equals 0 cap. I have already proved this vector identity in my lectures. Actually, in the part 5 of my lectures, I have proved this vector identity. The second vector identity is the divergence of curl f equals 0. In this identity, f is a vector field. So we can find out its curl. Curl f is also a vector field. If we apply the divergence operator on curl f, we get 0. So div curl f equals 0. I have also proved this vector identity in my previous lectures. That is, in part 5 of my lectures, I have proved this second identity also. So, first two vector identities are already proved. Now, let us take the third identity. In this third identity, phi is a scalar field. A cap is a vector field. So, phi a cap is the product of a scalar field and a vector field. It produces a vector field again. So we can apply divergence on it. Div of phi a cap equals grad phi dot a cap plus phi div a cap. Observe the RHS. In the RHS, grad phi is a vector, a cap is a vector. In the first term, the dot product between those two vectors, grad phi and a cap, produces a scalar. On the RHS, if we take the second term, that is phi div a cap. Div a cap is a scalar, phi is a scalar, their product is a scalar. On the RHS, the two terms are scalars, so their sum is also a scalar. The RHS of this identity is a scalar. Similarly, the left side div of phi a cap is also a scalar. Actually, this is a scalar identity since the LHS and RHS are scalar fields. Let us take the fourth vector identity. Phi is a scalar field, a cap is a vector field. The product phi a cap produces a vector field. Because it is a vector field, we can't apply gradient on it. Gradient can't be applied on a vector field. So we can apply divergence or curl operators on this vector field phi a cap. In the previous identity, we applied the divergence operator on this vector field phi a cap. Now in this fourth identity, we are applying curl on this vector field. Curl phi a cap produces a vector field. So the LHS of this vector identity is a vector field. Now coming to the RHS of this vector identity, the RHS is grad phi cross a cap plus phi curly a cap. Here also the RHS has two terms. The first term is the cross product of two vectors grad phi and a cap. The cross product of two vectors again produces a vector. So the first term on the RHS is a vector. If we go to the second term, the second term is phi curly a cap. It is also a vector. The sum of two vector fields is again a vector field. So in this vector identity, the LHS and the RHS both are vector fields. So this is called a vector identity. Whereas the previous identity is called a scalar identity. Now let us take the next vector identity, that is div of f del g. Here f is a scalar field, g is also a scalar field. Del g produces a vector field. F is a scalar field. F del g is a vector field. We are applying divergence on it. So div of f del g, it is a scalar. In this identity, the left hand side is a scalar. What it produces actually? It produces f del square g plus del f dot del g. If we observe the first term on the RHS, it is f del square g. F is a scalar. The Laplacian operator applied on g, that is the del square g, is also a scalar. Because f and del square g are scalars, their product is a scalar. Now take the second term on the RHS in this vector identity, del f dot del g. Del f is a vector field, del g is a vector field. Their dot product produces a scalar field. On the RHS, these two terms are scalars, so their sum is a scalar. The left hand side is the divergence of a scalar field. It is also a scalar. So the LHS and the RHS are scalar fields in this particular vector identity. So it is actually called a scalar identity. So among these 5 identities, we have already proved the first 2 identities. Among the remaining identities, 2 identities, 3 and 5 are scalar identities, but the 4th one is a vector identity. Let us take a 6th identity. In this 6th identity, let's consider 2 vector fields, say A cap and B cap. Their cross product A cap cross B cap produces a vector field. Because it's a vector field, we can apply divergence operator on it and also curl operator on it. The divergence of A cross B is the 6th identity. Curl of A cap cross B cap is the 7th identity. Let us first see our 6th identity. It is the divergence of A cap cross B cap is equal to B cap dot curl A cap minus A cap dot curl B cap. If we observe the LHS of this identity, A cap, B cap are vectors. Their cross product produces a vector, but the divergence of this vector is a scalar field. So the LHS divergence of A cap cross B cap is a scalar field. Now, if we take the RHS of this 6th identity, the RHS has 2 terms. The first term is B cap dot curly A cap. Curly A cap is a vector, B cap is a vector. Their dot product is a scalar. So, the first term on the RHS of this identity is a scalar. If we consider the second term, it is minus A cap dot curl B cap. Curl B cap is a vector, A cap is a vector, their dot product is a scalar. Altogether, the RHS is also a scalar. Hence, this 6th identity is a scalar identity because its LHS and the RHS are scalars. Now, if we go to the next identity, the 7th identity, in this identity, consider 2 vector fields A cap and B cap. Take their cross product. A cap cross B cap produces a vector field again. For this vector field, we can't find out gradient. We can find out divergence and curl. We found the divergence already in the previous 6th identity. Now in this 7th identity, we have to find out the curl of the same vector A cap cross B cap. So the LHS of this identity is a vector field. Coming to the RHS of this vector identity, it is A cap div B cap minus B cap div A cap plus B cap dot del A cap minus A cap dot del B cap. If we observe the RHS, there are 4 terms. Each term is a vector field. So the RHS is also a vector field. So this identity is a vector identity. Coming to the next vector identity, that is the gradient of A cap dot B cap. A cap is a vector field, B cap is a vector field, but their dot product is a scalar field. We can apply gradient on this particular scalar field. So gradient of A cap dot B cap is the LHS of this eighth identity. Gradient of a scalar field produces a vector field. So the LHS is a vector field. Coming to the RHS of this identity, we have B cap dot del times A cap plus A cap dot del B cap plus B cap cross curly A cap plus A cap cross curly B cap. There are four terms on the RHS of this identity. Each term is a vector field. So the RHS is a vector field. LHS is also a vector field. Altogether, this eighth identity is a vector identity. Here we have found the dot product of two vectors A cap and B cap. A cap dot B cap is a scalar. On this scalar, we can apply gradient only. We can't apply the other two vector differential operators, namely the divergence and curl. So we don't have curl of A dot B, we don't have div of A dot B. We have only the gradient of A dot B. Coming to the last ninth identity, in this identity, take a vector field A cap, find its curl. Curl A cap is a vector field. For this vector field, we cannot find out the gradient. We can find out the divergence and also the curl. If we find out divergence of this curl A cap, we get 0. That was our second identity. Here we find curl of curl A cap, which can also be represented as del cross of del cross A cap. Curl of curl A cap is a vector field. So the left hand side of this ninth identity is a vector field. Coming to the RHS of this particular identity, it is the gradient of the divergence of A cap minus del square A cap. If you see the first term of this identity, that is the gradient of divergence A cap. It can also be written as del of del dot A cap. It is del of del dot A cap. It's a vector minus del square A cap. These are our vector identities which we have to prove. Each identity is a theorem for us. Let us prove our vector identities. Each identity is a theorem for us. Before diving into the proofs of these identities or theorems, I would like to suggest you one thing. If you want to represent the dot product of two vectors or the divergence of a vector field, you have to make use of the Kronecker delta representation. To represent the cross product of two vectors or the curl of a vector field, we have to make use of the Levi-Civita tensor. Now, let us prove the third identity in the list as our first theorem, because I have already proved the first and second identities in my previous lecture, part 5. In this first theorem, we have to select a scalar field phi and a vector field a cap equals a1 I cap plus a2 j cap plus a3 k cap. We have to suppose that these two are differentiable fields. Since a cap is a vector field and phi is a scalar field, their product phi a cap is a vector field. Now we need to find out the divergence of phi a cap. Div phi a cap equals grad phi dot a cap plus phi div a cap. Let us prove this identity now. First consider our differentiable scalar field phi and the given differentiable vector field a cap equals a1 I cap plus a2 j cap plus a3 k cap. Instead of I cap, j cap and k cap, let us replace E1, E2, E3 respectively. So a cap equals a1 E1 plus a2 E2 plus a3 E3. Now multiply this vector with the scalar field phi and find out phi a cap. Phi a cap equals phi a1 I cap plus phi a2 j cap plus phi a3 k cap, or we can also write it as phi a cap equals phi a1 E1 plus phi a2 E2 plus phi a3 E3, that equals summation sigma over I phi ai ei. Now let us compute div of phi a cap. For this vector field phi a cap, what are the component functions? The component functions of the vector field phi a cap are phi a1, comma, phi a2 and phi a3. So div of phi a cap equals summation sigma over I summation sigma over j delta sub ij dou I of phi aj. This is the representation of div phi a cap by using the Kronecker delta. Now let us expand dou I of phi aj. Dou I of phi aj means the partial derivative of phi aj. If you put I equals 1, it becomes dou 1 of phi aj. That is nothing but dou by dou x of phi aj. If we put I equals to dou 2 of phi aj, that is dou by dou y of phi aj. If we put I is equal to 3, that becomes dou 3 of phi aj, which is nothing but dou by dou z of phi aj. In general, we write dou I of phi aj here. Now, div of phi a cap equals sigma over I, sigma over j, delta sub ij times phi dou aj plus aj dou phi. This is the product formula of the derivative. In this, the indices I and j take the values 1, 2 and 3. Now let us distribute the summations. Then we obtain the divergence of phi a cap equals summation sigma over I, summation sigma over j, delta sub ij phi dou I aj plus again summation sigma over I, summation sigma over j, delta sub ij aj dou I phi. We have to take out phi from the first summation. So we get phi times sigma over I, sigma over j, delta ij dou I aj plus sigma over I, sigma over j, delta sub ij dou I phi aj. That equals, if we expand the first summation in the first part, delta 11 equals 1, delta 22 equals 1, delta 33 equals 1. All the remaining delta values are 0. After expanding the first summation, we get 5 times dou 1 a1 plus dou 2 a2 plus dou 3 a3. All the remaining terms of the expansion become 0 because of the Kronecker delta definition. Plus, coming to the second expansion, sigma over I, sigma over j, delta ij dou I phi aj. This particular dou I phi is the ith component of grad phi. Aj is the jth component of a cap. This representation sigma I, sigma j, delta ij dou I phi aj is the dot product of those two vectors del phi and the a cap. So we obtain phi times dou 1 a1 plus dou 2 a2 plus dou 3 a3 plus sigma I, sigma j, delta ij dou I phi aj, which equals phi times div a cap plus del phi dot a cap. Del phi is also equal to the grad phi. So we get div of phi a cap equals grad phi dot a cap plus phi div a cap. We are done. In this theorem 2, I am going to prove the fourth identity in our list of identities. In this theorem 2, we consider a scalar field and a vector field. The scalar field phi and the vector field a cap equals a1 I cap plus a2 j cap plus a3 k cap are differentiable fields. Under these assumptions, we find out the curl of phi a cap. A cap is a vector field and phi is a scalar field, so their product phi a cap is a vector field. We need to find out curl of phi a cap. Here the identity is curl phi a cap equals grad phi cross a cap plus phi curl a cap. Let us prove this identity. Consider our differentiable scalar field phi and the given differentiable vector field a cap equals a1 I cap plus a2 j cap plus a3 k cap. Consider the product phi a cap equals phi a1 I cap plus phi a2 j cap plus phi a3 k cap. Replace I cap, j cap and k cap with E1, E2 and E3 respectively. So the product phi a cap equals phi a1 E1 plus phi a2 E2 plus phi a3 E3. This can also be written as phi a cap equals sigma over I phi ai ei. Now we need to find out the curl of this vector field phi a cap. The component functions of this vector field phi a cap are phi a1, phi a2 and phi a3. So curl of phi a cap equals a 3 by 3 determinant I cap, j cap, k cap on the first row, dou by dou x, dou by dou y, dou by dou z on the second row, phi a1, phi a2, phi a3 on the third row. But we know that dou by dou x equals dou 1, dou by dou y equals dou 2 and dou by dou z equals dou 3. Hence curl of phi a cap equals I cap, j cap, k cap, dou 1, dou 2, dou 3, phi a1, phi a2, phi a3. If we expand this determinant with respect to the first row, the first component or the coefficient of I cap is dou 2 of phi a3 minus dou 1 of phi a2. We represent this component with the symbol C1. Similarly, the second component C2 is the coefficient of j cap in this expansion. So the coefficient of j cap, that is C2 equals dou 3 phi a1 minus dou 1 phi a3. Similarly, the third component in the expansion of this determinant is given by C3 equals dou 1 phi a2 minus dou 2 phi a1. We know all these components. Instead of writing C1, C2 and C3, we write C suffix I in general. I takes the values 1, 2 and 3. So let C suffix I be the ith component of our curl of phi a cap. We represent the ith component C suffix I of curl of phi a cap by using the Levi-Civita tensor as follows. Ci equals summation sigma over j, summation sigma over k, epsilon suffix ijk, dou j of phi ak. In this representation, we have to apply the product formula of derivative for dou j of phi ak. If we apply the UV formula of differentiation for dou j of phi ak, the ith component Ci can be written as Ci equals summation sigma over j, summation sigma over k, epsilon suffix ijk times phi dou j ak plus ak dou j phi. Now we have to distribute the summations here. Then we obtain C suffix I equals sigma over j, sigma over k, epsilon suffix ijk phi dou j ak plus sigma over j, sigma over k, epsilon suffix ijk dou j phi ak. We must remember one fact here. We are finding the ith component C suffix I only. Here in this equation, the LHS is the ith component C suffix I. The RHS of this equation has two parts. The first part is sigma over j, sigma over k, epsilon suffix ijk phi dou j ak. From this first part, we can take out phi. Now coming to the second part, the second part of the equation is sigma over j, sigma over k, epsilon suffix ijk dou j phi ak. Here in this second part, we have to observe two terms especially. They are dou j phi and ak. Dou j phi is a representative from the gradient of the scalar field phi. The term ak is a representative from the vector field a cap. This second part is a representation by using the Levi-Civita symbol. If we use the Levi-Civita symbol, it is the cross product of the vectors. Here, a representative from the vector grad phi and a representative from the vector a cap participated. So, this representation is a cross product of grad phi and a cap. But we have to remember that this is just the ith component. Coming to the first part again, after taking out phi, we get phi times sigma over j, sigma over k, epsilon suffix ijk dou j ak. This representation is the representation of curl a cap, but we have to remember that this is only the ith component. As a whole, we obtain Ci equals phi times the ith component of curl a cap plus the ith component of grad phi cross a cap. Put p suffix I equals the ith component of curl a cap and q suffix I equals the ith component of grad phi cross a cap. Substituting p sub I and q sub I, we obtain c suffix I equals phi p suffix I plus q suffix I. This is the ith component of curl phi a cap. To get the entire curl phi a cap, we have to take the expression curl phi a cap equals c1 I cap plus c2 j cap plus c3 k cap. We have to substitute c1, c2, c3 here in this expression. We have found the ith component ci. If we put I equals 1, we get c1. If we put I equals 2, we get c2. If we put I equals 3, we get c3. After finding c1, c2, c3, we can substitute those values here. Otherwise, we can do one thing. Take curl phi a cap equals c1 I cap plus c2 j cap plus c3 k cap. That equals c1 e1 plus c2 e2 plus c3 e3. Then curl phi a cap can be written as curl phi a cap equals sigma over I ci ei. If we substitute ci value here, we can obtain curl phi a cap. So curl phi a cap equals summation sigma over I phi pi plus qi times ei. That equals sigma over I phi pi ei plus sigma over I qi ei. Now we have taken the summation over I. If we take this summation from I is equal to 1 up to 3, we obtain curl phi a cap equals phi times curl a cap plus grad phi cross a cap. We are done. Let us take our next identity as theorem number 3. This theorem 3 can be proved by using theorem number 1. In this theorem 3, we have to select two scalar fields. Suppose that F and G are two scalar fields. In this identity, we have the divergence of F del G equals F del square G plus del F dot del G. Let us prove this identity by using our theorem number 1. Consider two scalar fields, say F and G. First, let us find out the gradient of the scalar field G. Grad G or del G equals dou G by dou X I cap plus dou G by dou Y J cap plus dou G by dou Z K cap. According to our new notation, dou G by dou X can be written as dou g by dou x1, dou g by dou y can be written as dou g by dou x2, dou g by dou z can be written as dou g by dou x3. So, grad g or del g can also be written as grad g equals dou g by dou x1 I cap plus dou g by dou x2 j cap plus dou g by dou x3 k cap. But we have another notation. In that notation, dou g by dou x1 can be written as dou 1g. Dou g by dou x2 is equal to dou 2g. Dou g by dou x3 is equal to dou 3g. Now, gradient of g or del g equals dou 1g I cap plus dou 2g j cap plus dou 3g k cap. So we can understand that this del g is a vector field. I have already mentioned that we have to make use of theorem number 1 to prove this theorem number 3. What is our theorem number 1? The theorem number 1 states that if we have a differentiable scalar field phi and a differentiable vector field a cap, then the identity in theorem 1 says that div of phi a cap equals phi div a cap plus grad phi dot a cap. Now, in this theorem, we have two scalar fields f and g. We have found del g. Del g is a vector field. F is a scalar field. So let us substitute a cap equals del g and phi equals f in the identity of theorem 1. Then what happens? What do we get? Div of phi a cap on the left hand side becomes div of f del g, which is the left hand side of our present identity. In the previous identity, div phi a cap, the RHS is grad phi dot a cap plus phi div a cap. If we replace phi with f and a cap with del g, we get div f del g as our LHS and grad f dot del g plus f div del g on the RHS. We know that div del g is nothing but del square g. Then it gives us div of f del g equals f del square g plus grad f dot del g, or we can also write it as div of f del g equals f del square g plus del f dot del g. We are done. In this lecture, I have proved three identities. I suggest all the students to be familiar with the notations and the symbols like Kronecker delta and Levi-Civita tensor. For further queries, you can contact me through mail. Thanks for listening.